4 hours this afternoon. I've been on the beach for 3 hours this morning, so I'm hoping we'll do about 3 and survive. What I want to try and do today is to introduce ocean circulation and probably get through most of what I want to do so that I can start the modelling a little early this week and split it up, because it doesn't fit too well into next week's just single slot. So I'm going to try and make sure that I spread it out, because it's a little bit more tricky, I think, at times than the ocean circulation material. I'll also confirm with you next week's programme after the break, so that we can everybody knows exactly where we're at. And just to say, I'd asked you to sort of have available the paper on the Agulhas system, the nature paper. What I am aiming to do with that is to go through that paper with you to try and pick out the important bits about it. So it's really, if you've got a copy that you could annotate or look at in front of you later today, that would help. I will get it up here eventually. It won't let me get in through the internet without paying. So with the usual frustrations that we have with trying to access this stuff from the lecture theatres, so I've got a copy. I'll just put it up so that we can do the PDF through there. So that's what we're hoping to get through. What we're at the moment is we've done atmospheric circulation, so you have a bit of a basic idea behind how the atmosphere works, the vertical structure, the idea of Ferrell Hadley cells, intertropical convergence zone, general circulation. So in theory, we have behind us now the bit in the liquid above the ocean. Now we need to look at what's actually going on in the oceans and see how we can understand ocean circulation and begin to try and fit these two elements in together. So what I'm going to talk about is the structure of the oceans to begin with, in particular looking at issues of salinity and density and how it behaves, rather like how the air behaves. To look at then winds, boundaries, and the problems of the ocean, that there is land in the way, it is water, it isn't air, all sorts of other issues. And then towards the end we're going to look at circulation and key elements of circulation, the thermohaline circulation, but also I want to concentrate particularly on these other issues like the Agulhas issue. The thermohaline circulation looks as if it might be taking a back seat in terms of the way research is developing, so we'll need to move on a little bit from that as we go through. So oceans, right, 71% of the Earth's surface. High shortwave absorption, low albedo. We've talked about this already, the importance of this dark mass which doesn't reflect radiation particularly well, absorbs an awful lot of shortwave radiation and therefore is an enormous source of heat. And this is why it's tricky to understand the linkage of the ocean and the atmosphere, because so much of it is ocean. And the ocean is a complex body that we don't know much about and is difficult to monitor at the scale. So we have lots of evaporation and convection because there's a lot of moisture available. We know that the ocean system has a huge role to play in cloud generation, in storm generation. You can see where all these storms that we're getting at the moment, they're generating off the coast of America. They're all consistently generating. It's a very important component of the water cycle, and it's a route of energy loss via latent heat release. So it is a mode of energy transference that we need to understand how it happens. And effectively with latent heat, remember that you can get a change of phase without a change in temperature, although heat is absorbed. So if we get evaporation taking place into a cloud, that is effectively changes of phase and isn't necessarily change of temperature. And therefore when we get warming leading to raining out, again we can get a heat exchange, we can get energy exchange, but we don't necessarily get a change in temperature. So precipitation is the reverse of evaporation, and latent heat is released on this energy as energy during the phase change. So this energy transference, because we don't see, we don't feel temperature changing, we tend to forget that there is energy being transferred from one part to another part. So there is latent energy evaporated. That's another complication, because measuring latent heat is far more difficult than measuring temperature. So it's easy enough to monitor temperature change, but monitoring change in energy is far more difficult. That's why we tend to simplify matters into temperature all the time. We'll put that energy side just to one side though, because it's much simpler to deal with temperature with things that we can measure very easily, then we tend to concentrate on those sorts of changes and those sort of characteristics. That's especially important because when we look at the past, or we're predicting into the future, we can't measure past latent heat exchange. There's nothing to measure. Whereas we can estimate changes in temperature, we can estimate changes in pressure, well, we can change it in density. So, remember, atmosphere and oceans both fluids, so the same processes we get in the atmosphere will affect the oceans in the same way, fluid dynamics. It's a fluid. The oceans are fluid, therefore they behave the same way. We have pressure gradient acceleration, acceleration due to movement between different pressures. The old Coriolis comes into force with a big bang in the ocean currents. We have an idea of geostrophic balance related to the pressure gradient. And of course we have this Ekman transport, this spiraling transport, which is far more important in ocean systems than it is in atmospheric systems. So the same basic things operate. But we've got other complications. We've got surface wind, which affects the surface of the oceans. We've got the salinity of the oceans, which varies. The amount of salts varies across the ocean bodies as to what's in them. The atmosphere, we can sort of say, was a bit rough down the bottom, you know, where we get in the way and mountains get in the way. But once you get up higher, we can assume that there's nothing in the way. There's no real friction or anything. Of course, what we've got with the oceans are hugely complex basin depths. Huge depths, huge varieties in depths, huge variations in shape. We've got a ruddy great ridge going up the middle of the North Atlantic, gets in the way. We've got our understanding of the ocean floor is still not perfect. We probably, as somebody said, I think, we know the surface of the moon better than we know the base of the ocean, because we can measure it, we can photograph it, we can send people onto it, yes, but we can actually photograph the visible parts of the moon, no trouble at all. In fact, we can go around the back and use other techniques. But actually, our knowledge of the ocean basins is still, it's better, but it's still not perfect by any stretch. And we have also this lunar cycle, the impact on behaviour, especially on women, very strange behaviour and tidal cycles. I can tell there's a full moon in our house and everything starts going, whoa, and then it's all right for a bit. I haven't said that. I should probably get sacked for that, yeah. I certainly wouldn't be able to say that at home, my word. But the moon's gravitational pull, we know that tides are important. We know that we get tidal change. You know, we drowned the first year this morning. I tried to get them out into the low tide and get them out as far as they could, and they wouldn't go. But we're going to put that to one side because we can assume that the lunar influences are in a sense constant. They've been constant through time, they're likely to be constant through the time that we're dealing with, and they are mainly diurnal changes. So it's something which we know is there, but in a sense you can keep constant. So it's not something we need to really go into and understand in great depth and try to factor in to our understanding of the system. Pressure gradient is something we don't think about in the ocean. Again, we have this visual image of the ocean that it's a thing that goes up and down, swashes around and does all sorts of strange things. But we don't see it as a flat surface. We don't see it as a volume which in a sense operates as a flat volumetric surface. But if we had a uniform density of ocean water, then obviously we get movement from high pressure to low pressure in the water base. If the water's under higher pressure, it tends to push that water movement. The general movement tends to be from high to low, exactly the same as we get in air. And at any point, pressure can be estimated if we know gravity. We can put a figure on gravity. We know depth. and we've got an average density, so we can work out that. We can actually work out pressure across the ocean surface. Very simple, basic calculation. But density, which is a very important element of the ocean, is a fundamental function of two key elements which we need to understand and we need to factor in terms of understanding how things have moved in the past and how they're going to move and change in the future. So salinity, which is the dissolved salts, all kinds of salts, not just sodium, although that's the one that we tend to sort of think about, but all these elements getting into the ocean. The higher the salt, the greater the density. So in other words, the more stuff that's in there, the denser the water, the denser the water mass. And temperature, the colder the water, the denser the water. The denser the water, the more likely it is to sink. And sinking of water is very important to ocean circulation, the ability of water not just to flow, but actually to sink. And we know, therefore, that cold, high salinity water is more likely to sink than warm, low salinity water. So we can put numbers on this. We can actually estimate the numbers quite easily on this. And we can identify change in this as well. So average ocean salinity, 35 grams per litre, sometimes called PSUs, practical salinity units. What this means is that although the standard density of pure water is 1 gram per mil, the more you put in, the higher the density. So average density of seawater is 1.025 grams per mil, so it is more dense than pure water. But that means these two are obviously very different. This is the difference between fresh water and salt water. And the interaction between fresh water and salt water is an important element of change around the margins of land masses in particular, especially as you get into high latitudes where you get ice melting into fresh water. And we can identify, and this is something we'll